Okay, so we will continue after 2 weeks in the lectures of probability theory. And I just recall what we did last week, or last time, so it means 2 weeks ago. We considered the set capital omega with the elements small omega 1, omega 2, omega 3, and so on, where the small omegas were called elementary events. And in fact, it meant that when we have some random trial, the results, so it means the situations which can happen, are these elementary events. So, for example, I recall the example from last time when we threw a classical unbiased die. The elementary events can be omega 1, there is one spot on the die, omega 2, there are 2 spots on the die, and so on, till omega 6, there are 6 spots on the die. That's it. So the capital omega is so-called set of all elementary events. And when we talk about events, we mean some subsets of this capital omega. So for example, A can be a subset consisting of omega 1, omega 2. And in practice, it means, in fact, that the number of spots on the die is less or equal to 2. Or we can consider B omega 1, omega 3, omega 5, which in practice means that the number of spots on the die is odd. Consider set C of 2, omega 4, and omega 6 is then the event that the number of spots is even, and so on, and so on. Yeah, so when we talk about events, we mean some subsets of the set capital omega, and the set of subsets with some special property is called sigma algebra. Usually, we consider the set of all subsets of this capital omega, but it is not necessary that they are all. For example, when we care only about the situations whether the number of spots is odd or even, we can consider only the subset consisting of B and C. And for mathematical reasons, there must be also empty set and the whole set omega in this subset. And That's what we did last time. And we mentioned some properties, some terminology on these events. So, for example, we mentioned the intersection, the union, and their meaning. I recall that intersection of two events means, in fact, the intersection of the sets, for example, A and B. So it means the elements which are together in one and in the second set. And practically it means that both these events happen together. When we talk about the union, we means that the result of the random trial is in the union of these sets. So it means that either one event or the second event happened. And we mentioned also a complementary event. So it means that the complementary event of an event, let's say B, is the event which occur if and only if when B doesn't occur. So the complementary event to the event B in our case is the event C. And why do we have this terminology? The properties of the probability, which we will talk about, depends on this, or follows from these intersections and unions and this set theory. So when we define the probability as the function on the sigma algebra A, then it is a function which has the values somewhere between 0 and 1. Always it must be positive or at least equal to 0. And there is a property that the probability of union of so-called disjoint events can be calculated as the sum of their probabilities. Then other properties follows. So I just recall that we mentioned the probabilities, how to calculate the probability of the union of events, how to calculate the probability of complementary events, and how to calculate the probability of the difference of the events, and we talk about some other properties. Finally, we mentioned some special models we will consider in this lecture. We will talk about it in exercises, and now I will continue with other topic which is called conditional probability. So we still consider everything what is written here. We consider the set of elementary events, the set of usually all subsets of this set of elementary events. I will call it just briefly sample space. It will be shorter. And what does it mean? What is the meaning of conditional probability? The conditional probability is a probability of some event conditionally on some information about another event. So, for example, in our case, we want to calculate the probability of the event A conditionally on the event B. What does it mean? It means that we know that the event B occurred. We know that when we threw the die, the number of spots is odd. And we ask, what is the probability that the number of spots is less or equal to 2? Conditionally on knowing that the number of spots is odd. So, look, there are 6 elementary events when throwing the die. Omega 1, omega 2, omega 3, omega 5, omega 2, omega 4, omega 6. here we have the event A, here we have the event B. And we know that the probability that the number of spots is less or equal to 2 in general is equal to 2 over 6, because we have 6 elementary events and 2 of them satisfy that the probability is less or equal to 2. In our case, when we know that the number of spots is odd, means that the probability of even number of spots is equal to 0. But before we had this information, the probability of an even number was 1/2. So now we have 1/2 of probability which must be add something. And it is added to these odd numbers uniformly. So it means that now the probability of each even number is equal to 0, because we know that the number of spots is odd. So it means that we have the probability, total probability 1, which must be distributed between the odd numbers. So it means that the probability of each event is twice as large as the probability originally when we considered all these 6 events. Okay? So it means that we calculate the probability of the events satisfying that the number is less or equal to 2, but it must be also odd. And we divide it by the probability of the condition, by the probability of the event B. And because the probability of the event B is 1/2, and we need to have twice as large probabilities for these even numbers. Okay? So therefore we divide it by 1/2 in order to duplicate, to make the probabilities of these odd numbers twice as large. In this case, we get the probability 1/3, which is in fact the same as the probability of the event A without any condition. But when we consider opposite case, the probability of B conditionally on A, so it means what is the probability that the number of spots is odd, when we know that No. We'll consider another situation. We'll consider event D consisting of only one event. So we will consider small event D. And we want to calculate the probability that there is one spot on the die conditionally on B. So it means conditionally on the information that the number of spots is odd. At the beginning, when we have no information about whether the number of spots is even or odd, the probability of the event D is equal to 1/6. Only one possibility from 6 possibilities. But now, when we know that the number of spots is odd, so we know that only one of these 3 situations happen, is the probability of this event of event omega 1 in the total amount of events, but it must be divided by the event b, because the probability of each event is twice as large as the original probability. So the probability of one spot on the die conditionally on the information there is an odd number of spots is equal to 1/3. And when we consider, for example, probability of D conditionally on A, so it means what is the probability that there is one spot on the die when we know that the number of spots is less or equal to 2, then it must be 3 times as large as the original probability, because again we have some probability of the situations of the elementary events that the number of spots is at least 3, and this probability, which was original 2/3, must be uniformly added to these two events. So we expect that the probability is 3 times as large as the original probability, and really, when we consider the conditional probability from the definition, we get that it is 1/6 over 1/3. So it is 1/2. And it is from the reason that the probability of each elementary event in the condition must be 3 times as large as the original probability, because the number of elementary events is 3 times smaller than the number of elementary events in the whole set sample space. And so that's the meaning of the conditional probability, and the practical meaning is, as I said, we know that something happened, so it is written behind this line. And so the condition is written on the right side, and on the left side we write the event whose probability we want to calculate. Maybe it looks quite terrible, but it isn't, because in fact the conditional probability behaves like the normal probability. It is given by this theorem, which you can see, which says that when we consider a probability space, a random event B, whose probability is greater than 0, it is only because in the definition of conditional probability we divide by the probability of the event B. So in order this conditional probability is defined, we need the probability of the condition to be positive. And then for an arbitrary event A, these 3 conditions hold. And these 3 conditions are in fact the properties which define the probability. So when we prove that these 3 properties are satisfied, we proved in fact that this function is the probability in its definition, and we can work with this conditional probability in the same way as with the unconditional probability, with the classical probability. So what are these 3 properties? The first property is that the probability of the event A, conditional on B, is positive, or is not negative. probability of A conditionally on B is given by the relation probability of intersection of A and B over the probability of B. The probability of B must be positive. The probability of an arbitrary even is greater or equal to 0. So in fact, this ratio must be greater or equal to 0 as well. It's proved. The probability of the set omega conditionally on B is the probability of their intersection over the probability of B. But what is in fact the probability of all elementary events with an event B which is inside, which is the subset of this capital omega? It is B itself. So it is the probability of the event B over the probability of the event B, and it is equal to 1. That's it. The most difficult part of the proof is the proof of the property C, which says that the probability of the union should be calculated as the sum of probabilities. And again, we just add the condition B. But what does it mean, the probability of the union of AI conditionally on B? Or, okay, N, which can be also infinity. Consider the set A1, A2, A3, and there can be another event. I have no other color. A4, and we care about A4, and here we have our event B. The probability of the union of AI conditionally on B is, from definition, the probability of the union, I will write only the union of AI intersected with B over the probability of B. So from definition, it is the probability of the union of AI intersected with B over probability of B. But what is the intersection of B and the union of AI? It is the probability of the union of AI intersected with B. And because the union of AI intersected with B can be divided into these parts of B intersected with A1, A2, A3, and some other A's which we consider, over the probability of B. We know that in classical probability, the probability of the union can be calculated as the sum of the probabilities. So it is the sum of, again, over I, of probabilities of AI intersected with B over the probability of B. But this ratio is nothing than the probability of AI conditionally on B. So it is really the sum of probabilities of AI conditionally on B, and that's what should be proved, should have been proved. Yeah? So in fact we proved that all properties which define the probability are satisfied for the conditional probability as well. So it means that the conditional probability can be used in the same way as the probability unconditional. Here is the proof again. And now we will consider, or we will explain, another theorem. Due to my opinion, the best way how to explain something is to show an example. So I will start with an example. We have four black balls and four white balls in a box. We draw a couple of balls from the box four times. While we do not return the balls to the box. What is the probability that in each turn we draw one black and one white ball? So, how to solve this exercise? First, we can consider the events separately. So each turn will be a separate event. AI means that we draw one black and one white ball in the ith term for I equal to 1, 2, 3, or 4. Then we want to calculate the probability that in the first turn we throw one black and one white ball, and also in the second turn we draw one black and one white ball. The same must occur in the third turn and in the fourth turn. So all these events must occur together. Let's start from the beginning. We have 4 white and 4 black balls in the box. What is the probability that we turn one black and one white ball? The number of all possibilities how to choose a couple of balls from the total amount of 8 balls is 8 choose 2. Yeah? The number of couples, number of pairs from 8 elements. The probability that there is one black and one white ball is the number of all combinations of black balls with the white balls. So when we imagine, for example, the black balls to be denoted as 1, 2, 3, 4, and the white balls to be denoted as A, B, C, D, then the number of all combinations means the number of the combination of black ball number 1 with all white balls, the black ball number 2 with all white balls, and so on and so on. So it is 4 times 4 combinations. This is the probability that in the first turn we draw one black and one white ball. Then we have only 3 black and 3 white balls in the box. So it means that the probability that we again draw one black and one white ball is 3 black balls combined with 3 white balls over the number of couples made from 6 elements. And we will continue in the same way till the end. So now we have only 2 black balls and 2 white balls in the box. The number of all combinations of all pairs combined from 1 black and 1 white ball is 2 times 2. And the number of all combinations of all couples of balls is 4 choose 2. Then we have only 1 black and 1 white ball in the box. So formally the probability is given by this description, but in fact, of course, it is equal to 1. What is important? Not the result itself, but the way how we calculated the result. Because here we start with the probability of the event A1. It is okay. But this is not directly the probability of A2. But it is the probability of A2, which was calculated conditionally on knowing that we have only 3 black balls and 3 white balls in the box. And it is because we know that in the first turn, 1 black and 1 white ball were turned. were drawn. I'm sorry. The same happens in the third turn, in the third step. Here we calculated the probability that in the third turn we will draw one black and one white ball, but we calculated it from the numbers saying that only 2 black balls and 2 white balls are in the box. So conditionally on knowing that 2 black balls and 2 white balls were drawn before. And they were drawn is the event A1 intersected with A2. Yeah? In the last step, we have similarly the probability of A4 conditionally on all the previous events. And as we can see in this example, we got exactly what is said in the theorem on the slide. The theorem said that when we have a sequence, and there is a reason how to call them sequence, because you can see that we consider some time sequence. So we have for an arbitrary sequence of random events, A1, A2, and so on till AN, with the positive probability of the intersection. It is again given because we need the conditional probability to be defined. It holds that the probability of intersection of all these events is equal to the probability of A1 times the probability of A2, but conditionally on the information that the event A1 happened, times the probability of A3, again conditionally on the information that the previous events happened, and so on, till the probability of the last event conditionally on all the previous events occurred. What about the proof? The proof is quite easy when you know the definition of conditional probability. I will show you. I recall the definition of the conditional probability, which is given by the ratio of probability of the intersection over the probability of the condition. And we will use this relation in the proof in this form. The probability of the intersection is the probability of B times the probability of A conditionally on B. Okay? It follows directly from the definition. We want to calculate the probability of A1 intersected with A2, intersected with A3, intersected and so on, intersected with AN minus 1, intersected with AN. And when we denote this AN to be the event A in the definition, the intersection of the remaining events is the event B. Then, from the definition, we have that the probability of this intersection is equal to probability of AN conditionally on I will use it. In this form, but it is the same, of course. The probability of AN conditionally on intersection of all previous events times the probability of the event B, so it means the probability of the intersection of all the previous events. And again, in this probability, we can denote this last event as the event A and the intersection of the previous events as the event B. So we get probability of AN conditionally on all previous, the intersection of all previous events, times the probability of A n minus 1 conditionally on the intersection of the previous events times the probability of the previous events. And we can continue in this way. Again, we can denote it, the last event to be the event A, the previous events intersected to be the event B, and so on and so on. In this way, we go up, or we will get exactly the relation in the theorem. So that's the way how to prove the relation, which we in fact used naturally in the example before. So it is not difficult. The proof is just, it follows directly from the definition using the notation for our events in the sequence. And the theorem itself is also natural, as you could see in the example. So here in the slides on the web page, you can find the proof as well. And we'll continue with the next theorem. I will start with an example as before. And I will start with an example from our faculty. Let's suppose that there are 90% boys at Faculty of Electrical Engineering, and 20% of them have long hair. %70 of girls long hair. As well. And just in order to be correct, we suppose that for now we have only boys and girls at our faculty. So we have these informations and we want to calculate the probability that a randomly chosen student has long hair. The solution is very easy. It is, in fact, the probability or it is the ratio of students having long hair. And we know that when we meet a boy, or when we randomly choose a boy, the probability of having long hair is 0.7. When we meet a girl, 0.2 for boys. When we meet a girl, the probability is 0.7. But we cannot summarize this or make a sum of these two numbers. We need to make some average, but it must be weighted average because the probability 0.2 holds for 90%. While the probability 0.7 holds for 10%. You can imagine it on a sample of students. So when we consider 100 students, then in this 100 students, we have 90 boys and 10 girls. 20% of the boys have long hair, so it means 20% of this 90 is 18, and 70% of girls has long hair, so 7 girls have long hair, so it is 25%, 25 people from 100 students. Yeah, so therefore, we multiply the probability for boys and for girls by the weight corresponding to the ratio of boys and girls, respectively. So it is 0.18 plus 0.07, so it is 0.25, which is in fact the probability which can be calculated from this type. 25 people have long hair, and the total amount of students is 100, so 25 over 100 gives us the same result. We are interested in this calculation because I want to show you the meaning of the theorem which is presented on the slide. We want to calculate the probability that a randomly chosen student has long hair. So we will denote this event as the event B. We now, or we denote A1 to be the event that a randomly chosen boy a randomly chosen student is a boy. And A2, the event that a randomly chosen student is a girl. What is the meaning of the introduced probabilities? Zero 0.2 is the probability that when we consider a boy, when we choose a boy, the student has long hair. And 0.9 is the probability that we choose a boy. 0.7 is the probability that the chosen student has long hair when it is a girl. 0.1 is the probability that the student is a girl. And this is exactly what is said by the theorem. The theorem said that when we have some events A1, A2, and so on, and these events form so-called partition of the sample space capital omega. So it means that they are disjoint and they cover all possibilities which can happen, all events which can happen. And so it means that their union gives us the whole capital omega. In our case, when I said that we have only boys and girls here, we have the events A1 and A2, that a randomly chosen student is either a boy or a girl. Nothing else can happen. So these two events form the partition of the complete set capital omega. And we suppose that these probabilities are positive in order we can define the conditional probability. Then, when we know the probabilities of the event B conditionally on each of these events A, then we can calculate the probability of the event B itself, so without any condition, as the sum of all conditional probabilities which are weighted by the probabilities of the events in the partition. Yeah? So that's exactly what we got from this theorem. The proof of the theorem is very easy. when we consider the right side of the formula, the probability of B conditionally on AI times the probability of AI, it is nothing than the probability of B intersected with AI. It follows again from the definition of conditional probability B conditionally on AI, which is given by the intersection of B with AI over the probability of AI. And when we consider the sum till n or till infinity, depending on how many events we have in fact the sum of over I, the probability of B over AI. But again, when I draw the picture as before, so it means that we have some event A1, an event A2, another event A3, another event A4, and so on. What is the sum of intersection of B with AI? It is, in fact, the probability of B intersected with the union of AI, and the intersection of B with the union of AI is B. Yeah? So, in fact, the probability of B is equal to what is written in the theorem. On the next slide, you can find the proof again. And I think that the best proof for you was the example where you can see what is the meaning of this theorem. Okay, and now one of the most important theorems in this part of probability comes. It is called Bayes' theorem. Bayes' theorem shows how to calculate with conditional probabilities when we know the probabilities of opposed conditions. So it means that we must be very careful when calculating the conditional probability because we must concentrate on what is the condition, what is the information which we have, and what is the event whose probability we want to calculate. I again start with an example. It is a very actual example, as you will see, and it is the example from medical environment. it is known that 1 per mile of population suffers from a disease. The reliability of a medical test is very high, 99.5%. What does it mean, the reliability of the test? It means that the probability of the test to be positive if the tested person when tested person is ill, it means that he or she suffers from the disease, is 99.5%, so it means 0.995, and the same holds for the opposite case. So the probability of the test being negative if the tested person is healthy is 0.995 as well. The question is, when a person, for example you, have a positive test, what is the probability that the person is really ill? When his or her test is positive. So as you can see, it is very, very, very actual topic. And now, probably when you look at the reliability of the test, which is very high, you will see the positive test and you will start to panic because you are surely ill. But imagine the situation. Consider a sample of, let's say, 1 million people. The people are either ill or healthy, and their tests are positive or negative. We know that only 1 per mile of the population suffers from the disease. So it means that only 1,000 of, or only, it is not only, but in this sample, it is quite a small part. 1,000 of people are ill, and the remaining 999,000 are healthy. We know that when the person is ill, the test is positive with the probability 0.995, which means that 995 people are have positive tests when they are ill, and only 5 of them have negative tests. But what happens in this case? In the case of healthy people, 99.5% will have negative test, but there is still 0.5% of the people which are healthy and have positive test. 0.5% of these 999,000 is 4,995 people. And here is the rest, we don't care for it. Now, what does it mean? It means that in the sample of 1 million people, there are 5,990 people with positive tests. But only 9,995 of them are really ill. So it means that the probability we are looking for is 995 over almost 6,000, which is approximately 0.16. So there is the probability around 0.16, so around 16%, that you are really ill when you have the positive tests. And now we can describe the solution of this example by the theorem which I mentioned, by Bayes' theorem. The Bayes' theorem says that the probability of an event AI conditionally on the information B, conditional on the event B, can be calculated from the probabilities of the event B conditionally on AI using this relation. What does it mean? In our case, we want to calculate the probability that the person is really ill. So we denote A1, the event that the person is ill. For the theorem, we need the events A1, A2, and so on, which form the partition of the sample space capital omega. So it means that for A1, we need some other events A something, making the complete sample space, so making all possibilities which can happen. If the event A1 is the event that the person is ill, A2 is of course the complement that the person is healthy. What do we know? So we want to calculate the probability of the event A1. What we know is that the person has positive test. So we want to calculate the probability of A1 conditionally on B. And the Bayes theorem says that this probability can be calculated as the probability of B conditionally on A1 times the probability of A1 over the sum of probability of B conditionally on A1 times the probability of A1 plus the probability of B conditionally on A2 times the probability of A2. The probability of B conditionally on A1 is the probability of having positive tests when the person is ill. And we know this probability. It is the reliability of the test, so it is 0.995 times the probability of A1. What is the probability that a randomly chosen person is ill, or the person we chose is ill? So it is 0.001, 1 per mile, over 0.995 times 0.991 plus, now we need the probability of B conditionally on A2. We don't know exactly the probability that the test is positive when the person is healthy. But what we know is the probability that the test is negative. It is the complement even to the even B conditionally on A2. It is the reliability of the test. And we know from the first theorem of this lecture that the behavior of the conditional probability is the same as the behavior of the probability unconditional. So we know that the probability of B conditionally on the same event can be calculated as 1 minus the probability of the complement. So it means that the probability of B conditionally on A2 is 0.005. And the last probability is the probability of the event A2. So it means the probability that the person is healthy. And the probability that the person is healthy is 0.999 because it is again the complement even to the even A1. What do we get here when you calculate it numerically? 0.16 approximately. And in fact, when you look to these numbers, the numbers correspond to the numbers in the table. But in the table we have a sample of 1 million people. But when we choose the sample of 1 person instead of 1 million, we get exactly these numbers. Why? Because we work with ratios. And then when we work with ratios, it is not important whether we consider the sample of 1 million people 100 million people or just one person, which corresponds to the probability 1. It is the same. So when we look what these ratios, these probabilities or ratios means, here we have the ratios of ill people with positive tests, while in the numerator we have the ratio of people with who are ill and having positive tests, and the people which are healthy and have the positive test as well. So we divide the people with positive tests which are really ill by the people, all people with positive tests. And that's it. That's the idea of the Bayes theorem. We know the conditional probability in some situation, but we want to calculate the conditional probability which is opposite, where the even is the condition and the condition becomes the event whose probability we want to calculate. Okay, just briefly, the proof of Bayes theorem. I will show you the proof on this formula. So, sorry, I wanted to keep this. So, from the definition, we know that it is the probability of A1 intersected by B times the probability of B. But that's exactly the ratio here, because the denominator is equal to the probability of B from the law of total probability, and numerator is equal to this intersection from the definition of the conditional probability. The probability of B conditionally on AI is equal to this intersection over P over probability of A1. So therefore this product is equal to this intersection. The formal proof can be seen on the following slide. But more important than the proof itself is to understand what happens in these conditional probabilities. Yeah? Okay. So the last thing I will show you is the definition of independent events and the connection with conditional probability. So, in the literature, you can find two different definitions of independence of two events. The first one is which I introduced on the slide, that the probability of the intersection of A and B is equal to the product of their probabilities. Another definition which you can find is that the probability of A conditionally on B is equal to probability of A, because when A and B are independent, then B has no influence to the behavior of E to the event A. To the event A. So it means that the probability cannot be changed by the condition by the condition given by the event B, because they are independent. And really, when we use the definition of the conditional probability, we know it is the probability of their intersection over the probability of B. And using the first definition, the probability of the intersection is equal to the product of the probabilities A and B. So you can see that it is really the probability of A. And so these two definitions are equivalent, and it's up to you which one of these definitions you will use. For solving the exercises we have, this definition is more practical. Therefore, I introduced this definition on the slides. And it is the definition of the independence of two events, A and B. Of course, we can consider more events. So when we consider n events, A1, A2, and so on till An, then the independence of these events is defined so that the relation with the equality of probability of intersection and of product and the product of the probabilities must be satisfied for all combinations we can make. So this terrible definition means nothing than the probability of intersection is equal to the product of probabilities must be satisfied for all combinations we can get. So for example, for events A, B, C, and D are independent if and only if the probability of the intersection of all of them is equal to the product of their probabilities. But it is not enough. It must be satisfied for all triples and so on. And for all couples. And so on. Only and only if it is satisfied for all these combinations we can get, we can say that these events are independent. If at least one of these equalities is not satisfied, then the events are not independent. But what can happen is that all these couples satisfy the condition, the relation. Then we can say that the events are pairwise independent. So it means that all couples are the couples of independent events. But it can happen, and you will see on the exercise, that all these couples are the couples of independent events. Despite this fact, the events are not independent. And be careful, it can happen also opposite case, that let's say for the whole triple the relation is satisfied, but it is not satisfied for some of these couples. So there is no implication which says that if it is satisfied for some combination, it is satisfied for another combination. All crazy things can happen. So the events are independent if these relations are satisfied for all of them, and if it is satisfied only for couples and some of the other relations are not satisfied, we say that the events are pairwise independent. Okay, the independency for the events A and B imply also the independence for their complements, or for the combination of one of these events and the complement for the others. You can see the proof on the slide. And that's everything for today. So I thank you for your attention, and if there are some questions or comments, we will solve it on the exercise from temporal reason. Okay, thank you for your attention once again.